We're good.
We rolling, Dale?
Great history.
We're rolling.
Excellent. Thank you very much, y'all. Glad to see some faces we haven't seen in a while. Thank you for joining us at this February quote-unquote Cranbrook meeting. I am Diane Hall, your president. As far as club business goes, as you'll hear from the officer reports, we are starting to ease back into normal business with some outreach requests, some plans to do the statewide astronomy night in April. Riyadh's been doing the open houses, and I've been in contact with the actual Cranbrook staff about when we can and should get back into our beloved basement auditorium. So another thing of interest is to the overall community. If you have membership to the Henry Ford Museum in Dearborn, or you don't mind, buying a day ticket and a parking pass, they will be starting on February 18th an exhibit called When We Went to the Moon. That's about the Apollo years. So if you've not had the chance, check out their website, and I recommend that you go. As a member, I will definitely be going. Depending on what I find there, we may want to organize a field trip. The Henry Ford has been observing very good COVID protocols all through this. And depending on the time of day, it's pretty quiet in winter. So just wanted to let y'all know that. And big item, as some of you saw in the WASP, we lost long-term member John Root last month. I've delegated Adrian as treasurer to reach out to his insurance company to sort out the generous bequest that he left us. And we hope to do right by the gift. So Adrian will be following up with us probably next week. As you can see, Adrian's not here tonight. So at that, I'd like to pass things over to First Vice President Bob Tremblay.
Unmute yourself.
Helps to have this down, doesn't it? Okay, we got speakers through April. I need more speakers. If you'd like to give a lecture, give me a talk. One of the things that I'd like to suggest our members start looking at is doing presentations about individual space missions. And I think I'm actually going to be doing one for the March 5th meeting on the Europa Clipper. I gained some interest in that this morning, so more on that later. If I need more people to talk about stuff. I'm going to be reaching out to universities and stuff like that. I confirmed Deirdre Kelligan, an astronomical sketcher who is actually a blogger at the VOF as well, for June 16th. So I'll be following up with her. Other than that, that's it.
Awesome. And over to Riyadh, second VP, Stargate Beat.
Thank you, Diane. Hello, everyone. We had our last open house was January 22nd. The observatory was open from just before 6 o'clock till almost 9 o'clock. We had 3 members that visited, and unfortunately it was cloudy. So we just talked about the observatory, about astronomy in general, answered some questions. The next open house is scheduled for February 26th. So hopefully we'll see what the weather would be like. Of course, it's still winter, but I will be there unless the weather conditions are extremely dangerous or driving conditions, then it'll be canceled. But other than that, I will try to be there regardless. Couple of things, a few things to mention. We have discussed in the board meeting, and we voted on and agreed to purchase a few items for the observatory. One of them is atmospheric dispersion corrector, which would be great on our 8-inch refractor when we're looking at lunar planetary double star observing, if you're imaging or doing visual work. that usually should help quite a bit. That's something usually that we cannot correct for the way it is right now. The other thing is we're looking at purchasing what's called the Revolution Imager, which is a kind of a complete unit of electronic eyepiece and video display, so that we don't have to look through the eyepiece, at least while COVID is going on. And later on, it should also help when we have outreach programs. The other thing is we're looking at purchasing an ultra wide field binoculars, something like a very low power, so it's 2 by 54 millimeter binoculars with an extremely wide angle. This way you can also see an entire constellation with it. So supposedly these will go up to, I think, 34 degrees of angle, so pretty wide. So these are the things that we discussed, and hopefully once we have them, then we'll be able to use them. So look for them in the near future. That's all I have right now. Thank you, Diane.
Quite a lot. Thank you, Riyadh. Over to Mark at the secretary's desk.
Good evening, everyone. Just want to say the minutes of our January meetings are in our award-winning publication, The WASP, and that's all I have to report. Thank you, Diane.
Short and sweet. Thank you, Mark. Don't believe Adrian was able to make it tonight. His treasury report is in the WASP. He accepts payments by PayPal. If you did not renew your membership already, everybody's membership, barring those of some new members who just joined us in 2021, expired in 2022. So if you haven't yet kicked in your dues to Adrian, check out the mailer that you hopefully got in your mailbox that Dale Teamy sent out, or check our website to make sure what your rate is, whether you're a senior, student, family, etc. And Dale, Adrian will be happy to take your money via PayPal. You can also do a good old-fashioned check to the mailbox. The turnaround just takes a little bit longer. Okay, and with that, over to Kevin at Outreach.
All right. Marty Kuntz he needs help at a telescope party this Saturday, February 12th from 7 to 9 at the Hawkwoods Nature Center. So if you can assist, that'd be great. You can contact Marty or contact me and I can put you in connection with him. We talked a little with the Macomb Discovery Center, still trying to work out, connect with them. I'll be sending an email out to a list of people that I have who typically do outreach. I'm going to put all of their names just in the chat right now. These are the people I have right now. If your name is not there and you want to be on the emails that I'll send out to potential outreach, just send me your contact information. I'll make sure you're on the list. And that's all I have. And if anybody's not on the WebEx and you want to, just send it via the outreach at the Warren Astronomy, and I'll be happy to put you on the list. That's all.
Thank you, Kevin. Over to award-winning publications desk.
Okay, thank you, Diane. The WASP for February is up, and I'm delighted putting that together. We are well on our way to getting the March one together. So if you have something written that you wanted to have posted in the WASP, send them on into publications. And we're down to our last 3 calendars. So if you're on the fence about ordering a calendar, now's your chance. Thank you, Diane.
Thank you, Dale. Okay, so on to special interest groups. Solar Marty is not with us tonight. Now, the sun was absolutely hopping with sunspots as of last Wednesday. Bob, do you have a map for us? So multiple active regions, a whole lot of sunspots larger than the Earth. Definitely a get your solar scope of choice out and ready if you have clear skies, which today was a wash. Well, Bob gets that, over to Riyadh at the Double Star desk.
Yes. So at the next open house, once again, I'll have the list of double stars for the winter, and hopefully one of the things that we're going to be looking for, if it is clear, is Sirius B. So it is at Yeah, it's pretty wide open right now. It should be close to 11 arc seconds. That's the widest it will get. And hopefully we will be able to see that, but we'll see what the weather does. So be there if you can. It'll be a lot of fun. Thank you.
All right. Can y'all see these beautiful sunspots? Thumbs up, Dale or Riyadh, if you see the sunspots. Brilliant. Yeah, check these out, gang. It is good stuff right now. And I bet if you had a hydrogen alpha filter, it would look even nicer. Cool. All right. Thank you, Riyadh. Over to history group.
History group doesn't have a history.
We'll see if we can fix that for you.
Yeah.
Do we have the radio group tonight? Paul, I see your question in the chat. I will copy paste the information in the chat while the observing reports are going down. Okay, so we have a new radio subgroup chaired by Tom from the McMath-Hulbert group. McMath-Hulbert, as you may know, is no longer able to meet at their old site. So he and his prodigious gifts and prodigious equipment have asked to come on board as a new wave of radio activity in our club, which is awesome. So look forward to more of that coming down the pipeline. Astrophotography, I see at least one of y'all there. Mr. Buck.
Mr. Beers here.
Yeah, I don't
Even
have
better.
anything to report. CW Sirius Observatory is snowed in for the season.
Ooh. Bummer.
Yeah.
Yep. And in addition to, we're not snowed in, but we have only had 4 clear nights this year. So it hasn't been, I mean, I got a couple of photos for our observing report later.
Very good. Right. Any other subgroup reports? I think all the subgroup captains present have had their say. All right, over to observing reports. Raise your hand and let's get on it. I see 2 hands up from Dr. Levy. Take it away.
You need to unmute.
He's muted. You're muted, David.
I hope you can hear me now. Anyway,
Yes.
today, this month would have been Clyde Tombaugh's 116th birthday. And I remember observing Pluto with him at my old house long before Wendy and I got together, and also having a lot of fun. The sun, these days, the sun is wonderful, and I certainly agree with that picture. We have a lot of activity on the sun today, and no auroras from this far south, but the sun's being so active, there should be some pretty soon. On February the 18th, we're going to celebrate the 92nd anniversary of Clyde Tombaugh's discovery of Pluto, and we're still trying to decide what it is. For my quote today, I'm going to do this in honor of Clyde Tombaugh from the saddest part of his life. Believe it or not, after everything that that man did and accomplished, he was fired from Lowell Observatory. And the end of that particular chapter, I wrote, the telescope Tombaugh was finally about to leave stayed at Lowell, its long career not nearly over. Years later, director Arthur Hoag claimed that with its many projects, the 13-inch had become one of the world's most productive telescopes. If it had consciousness, it might have wondered about what would happen without a man it had shared a life with, a man who had never quite given up searching one more pair of plates for a hidden treasure, a man who called himself a traveler going over the next hill with an eternal hope. Thank you, and back to you.
That is very sweet. Thank you. Excuse me. As Doug said, we have had all of 4 clear nights lately. Who's had a chance to observe and what did y'all see? Riyadh.
Yeah, lately I've been projecting the sun and looking at the sunspot this way and showing it to the family. It's been very easy, very nice, and wonderful to once again see sunspots all over the sun and all the time, easily seen now.
I saw some. I was particularly enamored with the show Venus put on more recently in the morning. It's very, very bright right now. And as I was mentioning earlier on, there was some Earth light, Earth shine on the back of the moon pretty much all this month. I saw one a couple of nights ago, and then I saw that at the same time that I saw Venus. And just as going out there and looking at it, it was very, very cool. And Jupiter, I guess, is setting right now. And Saturn's on the other side of the moon, the other side of the sun. So kind of cool.
Very good. Bill Beers.
Yeah, I haven't really done any observing here in Michigan. Like I said, we're snowed in up north. A couple weeks ago, the wife and I were in southern Mexico, where it's 15 degrees latitude. And one morning I got up early because I wanted to see the Southern Cross, and it's about 10 degrees up. So that was pretty cool. And then along with all the stars in Centaurus, and then Omega Centauri, which was pretty bright. That happens to be the closest star to us, by the way. And one constellation below Crux that I've never seen is Musca. The Alpha and Beta stars in Musca. So that was pretty neat. I mean, and everything down there at those lower latitudes, everything is up pretty high that we're used to seeing here. Everything's up really, really high. So it was kind of a real treat to look out over the ocean and see the Southern Cross there. Pretty neat.
That does sound like fun, Bill. Jonathan and I will be headed down to New Mexico to meet up with an old friend who used to work at Los Alamos. So we're only bringing a pair of binoculars, but hopefully we'll be seeing something nice there from Albuquerque.
Oh yeah, you should be able to see Omega Centauri easily from there, I would think.
Yeah, we were able to see it from the latitude of Vegas, so Albuquerque should be no problem, especially this time of year.
Yeah.
So should be good. No Southern Cross though.
Yeah.
All right, who else has some observing reports? Near or far? Doug Bach.
So, it was clear the nights of the 2nd and the 3rd and the 21st of January, for at least for here, with temperatures that were tolerable. Sub-zero temperatures. I don't even open up the observatory, nor do I go outside actually. So when it got to minus 16, I wasn't even interested in going out. But anyhow, I'll just show a couple of things that I took. This was on the 3rd, was the double cluster using the William Optics refractor I got in September at f7. So this is H. Persei, and it's kind of a neat shot. And then, excuse me, I went after IC 405, which is the Flaming Star Nebula, which is in Auriga. And
Doug, you're not sharing your screen.
Yeah, we're still seeing the horse head, Doug.
that's interesting. How did that happen? Still seeing the horse head. Oh, I shared the wrong screen.
Yep.
Sorry about that. Hang on a second here. Share. This one. Thank you for that. And let me bring this back up here. Okay, so this was the double cluster.
Nice.
With the refractor, which is in the WASP. I believe this is the one I published in the WASP. and then which I just talked about, and then there was the star flaming star nebula IC405, which is an Auriga. And this is an emission and reflection nebula. It has both emission and reflection. The little blue around this star here, which is AE Auriga, which is also a bluish star, and it's illuminating a lot of this. So you're getting reflection and then emission lines coming off of all this nebulosity that's around there. So that was kind of neat. And this one was taken on the night of the 21st.
Hey, Doug,
That's-
what telescopes did you use for those 3 images?
My 105 millimeter William Optics.
For
F7.
all 3?
Yeah.
Okay.
Yep. This one, and the cluster. Yep. The double cluster. Those are all the same approximate. And this was the ASI 2600 one-shot color camera that I'm using on there. Okay.
Looks good.
It does.
That's my report.
Excellent. Who else? All right. Well, we got a little treat. Mark, do you want to tell everybody about the door prize next week?
Yes. The American Astronomical Society was a little late in sending their donation, but we do appreciate it. At the Macomb meeting this month, I have a list of the people that won door prizes at our winter banquet. So any other member that didn't win a prize or didn't apply for it, they sent us this Binocular Highlights, Gary Saronic. This is one of my favorite articles in all the Sky and Tell. So that's what this is culled from. So this will be the door prize at the Macomb meeting this month. That's it.
Thank you, Mark. All right. I've no additional observing reports. I see some people raising their beer glasses and wine glasses and such. Yep. Cheers, everybody. We can break for 15 minutes and see if our first presenter of the night is ready to roll. Sound good? See y'all at 8:15.
Mr. Ross, can you hear us?
Weird. Can you hear me?
Yeah, I can hear you. Is this Clay?
Yep, this is Clayton.
Hey, Big Joe and I want to know what Gary's serving for dinner over there.
We had pizza, thank you.
Okay.
But you should just announce the video and play it, since I'm not really geared up for to broadcast audio. I just threw on this headset a minute. But just play it whenever you're ready.
We will go live at 8:15 if that's okay with you.
Whenever you're ready.
Perfect.
Sounds good.
And Gary says, Bill, that it was the same pizza you had last time.
Oh, perfect. Excellent.
But yeah, enjoy the little movie clip. I
All
hope
right,
you all
we will.
like it. Bye.
I did pick up a few more things last month. I just didn't think they were worth going over.
Well, you can
Well-
share them with us now, Doug. We don't mind.
What did you buy?
Pardon me?
You said picked up a few things, as in new equipment.
No, just pictures I also took. I mean, I
Oh, gotcha.
got the I went after Comet Atlas L3 here on the 2nd. Just a little fuzzball with a little bit of a tail on it, not much. I went after IC 342. These are all with that 4-inch refractor I've got. That was taken on the 2nd of January as well. And of course the Star Nebula. This was just also with the 4-inch refractor. This is on the 3rd, morning of the 3rd. Just experimenting. I'm experimenting with this scope since I've gotten it to see what kind of things it can do, and etc. So,
In general, have you been happier with it than your RC, or it's the new thing and you're checking it out?
it's the new thing, and it's also got over twice the field of view.
Yeah,
So that's really the reason I wanted it. I'd been looking at getting something with a wider field of view, somewhere in between my 300 millimeter and my 2000 millimeter, and this one's running at 735. So it seems to be a nice format for clusters of galaxies. For example, the Leo triplet will be probably pretty nice in that. I don't think it's any better or worse than my RC. I still love I'll be putting my RC back up on for galaxy season. Yeah. Oh yeah. But
I never took my SCT down. I thought I'd put my other one on for winter, but I've just been distracted with so many other things. I haven't really got to work on that, so
yeah.
It's still up.
So this is MEL 15 and IC 1805 are basically the Heart Nebula with an open cluster in the center of it. Again, with that same 4-inch. I've been using the 4-inch since I got it. I started using it in Oklahoma in October. I was down there taking 10-minute shots. But these here that I'm showing you are from my backyard. And we already went through these. That was it. That's all I got for this last month. We've had some teasers, weather, where it says, "Oh, it's clear, but oh, it looks like high stuff's coming," and then it clouds up within an hour. So I didn't bother to open up. Ken's got my lunar eclipse shot up there. Oh, that's the other thing. In May is the next lunar eclipse we can see from here.
Total?
Yeah. I think it's May 18th.
Well, it looks like I may have just pulled the trigger on a solar scope. One came up on the forums and I kind of jumped at it.
Yep. May 18th through the 19th. It'll be total here.
Maybe a little bit, it might be above freezing this time, huh?
Yeah, it might be. Yeah, it was pretty cold back then on the January 20th one.
But the one like 2 years ago.
Hey,
It's in the
Gary Ross,
-5 or whatever.
If Gary Ross is looking, I think he'll appreciate the fact that I actually got this Book of All Knowledge.
Didn't Diane show one of those the other day?
Which one?
Observer's Handbook 2022 edition.
Oh yeah,
I got the Book of All Knowledge.
I got one of them.
And the funny thing about that is I haven't had one for so long. Oh, I hurt my back recently, so I've been kind of discombobulated lately.
Hey, Doug, I've got a question for you.
Yeah.
On your refractor versus your reflector, do you find that you get relatively equivalent resolution if you crop the images from your refractor?
No, the 10-inch is much better resolution.
Is it? Okay.
Yeah, well, it's over twice the focal length, so the only limiting factor on that 10-inch is really the seeing.
Well, that's what I'm finding here, that the seeing apparently is a limiting factor. I'm just comparing my 8-inch LX200 to my 115 millimeter refractor, and I'm finding they're pretty comparable, and I crop them equivalently. The refractor is a little undersampled, but I can fix that with drizzling.
Well, the same camera on my refractor is almost exactly 1 arcsecond per pixel at that focal length.
Mm-hmm.
Whereas on the 10-inch, it's not quite 4/10 of an arcsecond per pixel. So I'm oversampling a little bit, which makes the stars smoother looking. Except for the fact that I've got.
Do you ever get seeing that good?
No, hell no.
So what's the point?
Well, the point being is I can't buy a big enough chip with big enough pixels to go 1-to-1.
Yeah.
That I can afford.
Well, I guess what I'm getting at is why not just use well, I guess the refractor is a smaller aperture, so there's your difference to get better light grasp.
It's a 4-inch refractor. It's only 735 millimeter focal length.
Yeah.
The 10-inch is 2,000 millimeter focal length, so I've got better magnification. So it's just, well, I haven't really looked close. I suppose if I took some images of the same object in the same night with both scopes, with the equivalent type acquisition, that'd be an interesting comparison.
Yeah, I just did that, and I was quite surprised. My processing is a little better than it was 2 years ago when I shot my comparison image, but it was an interesting comparison. I actually compared my refractor with the reducer on it, which is 644 millimeters, to 1260 with the LX200.
Well, the reason I put the 10-inch on for galaxy season so I can get the magnification. I'm not really looking for. Let me put it this way: the 10-inch is seeing better than the seeing allows.
Mm-hmm.
So my resolution is pretty much limited to the seeing. So when you get around 2 arcseconds seeing on average, it doesn't really matter which one you use.
But Doug, your resolving power goes up, right, with the aperture?
Oh yeah. But I've got a bigger obstruction. I got a big obstruction in the 10-inch. But still, it is better. It's a better details on the galaxies. That's what I use it for. I mean, I don't think. Let me pull one up here, and I'll kind of give you an example of what I'm talking about. I mean, this has taken almost 3 years ago, before I even had my processing down. But this is the size of M51 with the 10-inch. I mean, you can get good sizes on some of these galaxies. Oh, yeah, I'm sorry. Another brain fart. So this is the galaxy with the 10-inch. This is, I can blow it up and looking. This was a possible supernova possibility in M51. That's the reason it's blown up. But I mean, that's the 10-inch. And this isn't even good processing. I got noise in it. I got a trail. This is back, 3 years ago before I started using flats and stuff. I should go back to this data and reprocess it again. So anyways, that's just an example of the scale that you can get with a 10-inch where you can't get it with that 4-inch. It's like 60% more magnification, 70% almost. So it'll be going on soon. I do want to make a next clear night I get. I want to make a run on the triplet in Leo before, yeah, it means doing it in the morning hours, but that's okay. I just got to get clear weather to do it. Meanwhile, my buddy Gordon Miller he's camping down in New Mexico there near Rusty's RV park. He's getting clear nights there every night.
Where's Rusty's RV park, Doug?
It's right. You know where Portal, Arizona is?
I know nothing about New Mexico other than I went to Albuquerque once 40 years ago.
So it's right down at the southwest corner of New Mexico.
Oh, okay.
It's well below Albuquerque.
It's dark.
Oh yeah, it's Portal 1. That's why there's astronomy villages down in that area.
Yeah, we're just flying into Albuquerque and going to be poking around Albuquerque and Santa Fe. So
yeah. Well, Rusty's is where I want to go during the winter. I didn't go this year for family reasons, but I still want to get down there. Actually, if I could get the trailer out of the backyard this month, I might go down there for March and April. Well, we'll see.
Diane, are you guys going to plan on heading south at all from Albuquerque?
we talked about it initially, but after looking at the drives and looking at what our time frame is, we decided we're going to do southern New Mexico properly at a future trip. So like do El Paso, do Las Cruces, do White Sands, and all that stuff. So this is just going to be the north. So Sandia Peak, petroglyphs, the cultural stuff, architecture.
We were just out there and we visited a wildlife refuge that we were kind of surprised at how good it was. And we got there and we found out that it is considered the crown jewel of the wildlife refuges. And I thought you might like to hear about that.
Is that the one right off I-25?
Not off the interstate, but it's...
Is that the one off I-25 south of Albuquerque?
Yeah, but it's pretty far south.
Okay, if you can send me the name, I will see.
It's called Bosque del Apache.
Oh, okay, that's not the one I was looking at. I'll check it out.
It's near Truth or Consequences.
Oh yeah, Jonathan really wants to go to Truth or Consequences, but I don't think we'll be able to fit it in this time.
And the VLA, Very Large Array.
Yes.
I don't think they're giving tours right now because of COVID.
Right.
I was there years ago. It's a fascinating scenery, just to see the site. But if you are in the region of Truth or Consequences, don't skip that wildlife refuge. It's the best I've ever been to. So
Good. Well, we fully intend to get back there and hit the southern part of things. So
yeah,
we'll see how it plays out. Thanks for the recommendation. And I am told that our video that's going to be our first presentation is in fact ready to go. Give you all a 2-minute warning since we're convening just a little bit early. So 2 minutes, come on, get back to your seats, mute your audio. Cheers. And we will be ready to roll shortly.
Diane, I believe Dale was going to play that. I wasn't planning to share it directly.
Yes. Yep, he says he's ready to go, so I'm just giving everybody.
Okay, I just saw I didn't have his camera on. I was a little worried about that. Thank you.
Thank you. All right. Is our host ready to roll?
Ready to roll. Want me to just go ahead and start it?
Bob, do you have an introduction to give, or will the
I
feed speak
could
for
read
itself?
what's in the WASP. Other than that,
Go ahead and share it, at least.
Let's do that, please.
okay. Well, I'll go ahead and read this here. So, our presenters, our video presenters, are Gary Ross and Clayton Carey. According to what's in the WASP here, while much deserved attention has gone to the Mayan study of astronomy, the ancient peoples of Peru has not. Last July, as it happens, the daily magazine show of the CBC Radio 1 conducted an interview with a Peruvian archaeologist. Oh my goodness, Ivan Getzi, I hope I didn't mangle that, regarding the recent work at a stunning site. This journalism deserves more attention, and if Gary says that, he's going to give it more attention. So take it away, Dale.
Deep in a desert valley in Peru lies the Chanquillo, an ancient fortified complex made up of several buildings and including 13 protruding ridges on a hill that look like the vertebrae of a giant buried monster. They're not, though. They are thought to be the oldest solar calendar in the Americas, built over 2,000 years ago by pre-Incan Peruvians to track the days and study astronomy. And this week, UNESCO declared the Chanquillo Observatory to be a World Heritage Site. Ivan Getzi is the program director of the Chanquillo project. We reached him in Lima, Peru.
Ivan, you've been pushing for this UNESCO recognition for years, so how are you feeling now that it's been awarded?
I'm overwhelmed with emotion. It's been a few years of work. We have faced great obstacles, always, of course, with the support of the local city, the citizens of Casma, and all of the people who work with me at the project. And now that we have achieved this recognition for Chanquillo, we are incredibly grateful. We are humbled by the honor, and we look forward to the next decade to make this all the potential of Chanquillo a reality.
And so for people who aren't familiar with the Chanquillo, can you explain a little bit about what it looks like and how important it is?
Yes, imagine a giant ruler in the sky. These 13 towers that were built on top of a small hill are positioned in such a way that when viewed from the observing points, the place that I like to call the Astronomers Chair, they become sort of a positional instrument that matches exactly the range of movement of the sun across the horizon throughout the year. So for instance, the southernmost tower, which we call Tower 13, aligns perfectly with the sunrise on the December solstice. And all the towers in between mark dates for every day of the year with a precision of 1 or 2 days.
Mm. And how big is it? Because I'm looking at a photo of it and it's hard to really understand the scale. It almost looks like I'm looking at a lizard's tail.
Yes. A lot of people like to call it the spine of the dinosaur or a lizard's tail. It's everything about Chanquillo is monumental in scale. The towers are between 3 to 8 meters tall. The fortified temple, which is another sector of the site, is 300 meters across with walls that are 6 meters wide and 8 meters tall. Everything is on a really grand scale. And this was necessary to create the positional instrument that the towers are, to create a lot of different angles and vertices that offered many positions to be able to match or align the sunrise or sunset with the visible eye, with the naked eye, and the day.
You just explained a little bit about why it was made, but what do we know about the people who built this temple, and also how and how difficult it was to do?
It is very important to recognize that we are at the beginning of research and scholarship at Chanquillo. We do not know enough about the people who built it. Obviously, they worship the sun and they had the incredible ability to gather enough public labor to build this monument in a relatively short time. But we do not yet know what language they spoke, how they buried dead, what they ate, or where they lived. So there's much more to do.
And now that you've gotten this UNESCO recognition, will that help in, for example, getting the resources or funding or the people who can help uncover this work?
I think this recognition is already attracting a lot of attention, and certainly we hope that more people will come together and realize the importance of developing this site for visits and of safeguarding it for the future generations. But there's an even broader impact. I come from a country that is often described as part of the third world or underdeveloped. And we Peruvians are taught in school that our contributions to the rest of humanity were the domestication of potatoes and other crops, or today we are seen only as a source of minerals, fish, oil, and not much else. But with the recognition of Chanquillo as an ancient observatory, one of the oldest in the world, probably the oldest, and definitely the earliest in the Americas, as the recognition of Chanquillo as a birthplace of astronomy, Peruvians realized that we were a civilization that was practicing sophisticated astronomy and built this positional instrument with the combination of architectural, astronomical, and technological knowledge that UNESCO has recognized as a masterpiece. So we look forward to the future with a different outlook, that we can regain that great place in human history.
Right. This is so fascinating. I mean, to think about over 2,000 years ago, this system of time and astronomy. And, you know, does it impact how we understand astronomy and time today?
Absolutely. We are used to think of astronomy as a science that is based on optical and radiological instruments. But there are earlier forms of astronomy that are just as important and just as scientific. This is a type of positional astronomy or horizon astronomy that actually exploits the knowledge that in relationship to the horizon, the sun, the moon, the constellations, the stars actually travel in relationship to the horizon. And these movements are part of a great clock that is the universe, a system that repeats these cycles year to year. So that knowledge can be exploited to mark the dates according to the position. And this is just as scientific as the type of astronomy that we do today. Perhaps the difference is that in the case of Chanquillo, for instance, this was science in the service of a broader ideology, the cult of the sun. But it was empirical. I'm sure that they had, many observations to make before they could build the towers. They made sure that the climatological conditions were perfect. They made sure that they had two observing points, one for sunrise and one for sunset, so that they could have two chances every day to make the observations that they needed. So clearly they were doing very sophisticated scientific practices, and that is amazing because this site is 2,300 years old.
It is truly fascinating, Ivan, and I can't wait to learn more about Chanquillo, and hopefully with this UNESCO heritage designation, we will learn much more in the coming years. Good luck with your research.
Thank you very much.
Ivan Getzi is the program director of the Chanquillo project in Peru. We reached him in Lima.
Okay, I've put a whole bunch of links in chat
I
about the
see.
site.
Thank you, Bob. So for those of you who haven't looked at the chat, Bob has thankfully put in a link to the observatory itself, to the NPR story, to the WMF.org project on the Chunquillo Archaeoastronomical Complex, and an article in The Guardian talking about how it was awarded a UNESCO World Heritage status for being the oldest solar observatory in the world. And this was a site I was not aware of until y'all brought this in. So thank you very much, Clayton and Gary, for doing this. Okay, Bob,
Dale, you ready to go?
yeah. Do we have any questions about the film? Dale Parton.
How can it be, if I got it right, that observatory, I think I heard him say, was about 2,000 years old?
Article says 2300.
Okay, 2,300. So that would make it something like 300 BCE, give or take.
Yes.
Stonehenge goes back to 3,100 BCE. So I agree it may be the oldest in the Western Hemisphere, but not in the world.
Well, he did clarify that. He said in the Americas.
Yeah.
And he said, and maybe in the world.
So, well, maybe. So the maybe was a guess.
Maybe I shouldn't have mentioned it. So should I get going?
Yeah, I'm gonna do the intro here. Our next speaker is Dr. Dale Parton. He's been a you're president, right?
No.
No? Well, he was first vice president. He's given several presentations. I think the most impressive ones that I've ever seen are these ones like he's doing tonight, where he's doing calculations on his own using observations. So, from the WASP here, in the ancient world, it was common to think about celestial objects in astronomical terms or astrological terms. Eventually, a new school of thought began among some Greek philosophers who thought that celestial objects were perfect heavenly bodies, objects that obeyed fixed laws. These Greek philosophers reasoned that mathematics and physical measurements could be used to determine the size of the Earth and the distance to the Moon and the Sun. Dale wanted to understand and replicate these measurements. His work and results will be described. Take it away, Dale.
Okay. How's that look?
Wonderful.
Yeah, good.
Okay. So, measuring the Earth, the Moon, and the Sun the ancient way. I might say that I happened to get an astronomy book published in 1898, which gave it was like the history of astronomy, and it gave some idea of how the ancient Greeks had done these kind of measurements and sucked me in. This was back in 2005. So I did a bunch of measurements back then, and gave a sort of preliminary report in 2006 to this august body, the Warren Astronomical Society. And I thought it might be good to go over this again, and I put a fair amount more material into it. So that's how this came about. Uh-oh, my down arrow key is not at phone. Okay. So, in the ancient world, as you heard in my abstract that Bob read, people thought about celestial objects in mystical astrological terms. The gods of the sun, moon, and stars and planets ruled from the heavens. and could influence things on Earth in unpredictable ways. The sun was especially powerful. He determined things about your life depending on which constellation the sun was in when you were born. The moon was also particularly important. So belief in these heavenly gods caused people to not think very much or trust in physical causes of things. A pattern in nature might not always stay the same if a god intervened and changed something, so this inhibited the development of scientific type thinking. In the picture, you see a temple in Mesopotamia of Nana, the moon god, who is written about in the earliest writing from that part of the world in 3500 BCE. And I thought this quote at the bottom is kind of interesting. It's from the Bible, the Old Testament. Beware lest you raise your eyes to heaven, and when you see the sun and the moon and the stars, all the host of heaven, you be drawn away and bow down to them and serve them. So it's obvious that some people were doing that. So there came to be the beginning of ancient Greek philosophy, which encompassed what we would call science. Some ancient Greeks went to Babylon and Egypt, the earlier centers of knowledge that they had access to, and learned from them. They returned to Greece and began to improve on that knowledge. A school of philosophy gradually developed based on reason and causality, but as you will see, still very much mixed with astrology. The Greek philosopher Plato referred to the sun, planets, stars, etc., as the visible gods. Plato's student was Aristotle, and both of them advocated starting with first principles and obvious truths. And from those first principles, you then logically deduce additional truth. The model for this was geometry, which was the Greeks were pretty strong on. You start with axioms that you're sure they're true, even though you can't prove they're true. And then from those axioms, you derive many theorems. And for geometry, that works pretty well. Although Einstein invalidated at least one of the axioms of their ancient geometry, because space is curved near a massive object, and that causes problems, or requires geometry to be generalized. So what they had is not the scientific method, but it does involve cause and effect. So here's a list of the first principles that Aristotle held to. They're generally wrong. If you start with a wrong starting point and then start deducing things from that, you know there's going to be some problems. So first, Earth is imperfect and changeable, but the heavens are perfect and unchanging. Why would that be? Because that's where heaven is and gods are, that kind of thing. Earth was at the center of the universe, geocentrism, that's called. The sphere is the perfect shape, and therefore, if heaven is perfect, things have to involve spheres and spherical motion, that sort of thing, up in heaven. The moon is at the boundary between the perfect and the imperfect. I assume they said that because you can see vaguely some imperfections on the moon without a telescope. Celestial bodies, like the sun and the moon and the planets and so forth, were attached to crystalline spheres that were perfectly transparent that orbited the Earth. So these spheres rotated, and each planet was on a different sphere that rotated at a different rate. A guy named Eudoxus, Aristotle had a complex set of interacting crystalline spheres that was needed to explain some odd features of celestial motions. And celestial objects moved with perfectly uniform, constant motion, constant speed on these spheres. So that was obvious truth to them. Just to show an example of why it was difficult to make this understanding work, here's a picture that shows the retrograde motion of Mars in 2016 and in 2018. I mean, it's difficult to explain that motion when all you've got is spheres that are rotating, carrying Mars on its surface, rotating with constant uniform motion. Now, how do you do that? Well, you have to make things complicated. So here's a model that Eudoxus had for the motion of one planet. You had an outer sphere rotating in about a certain axis, another sphere rotating attached to some point on that one, but rotating on a different axis inside it. Here's another sphere rotating on another axis, and of course, Earth in the center. So if you do that, you can make a planet do strange things. He used 27 crystalline spheres for the sun, moon, and the 5 known planets. Aristotle later expanded this to 55 crystalline spheres to make it better match observations. And all of these spheres had to turn at different rates and different angles. Kind of complicated. There was a notable exception, a philosopher named Aristarchus, who lived about a century after Aristotle. He proposed, amazingly, that the Earth rotated on its axis and orbits the sun. Virtually no one believed him. Aristotle was a giant figure, not only with regard to astronomy, but many other fields. And he was trusted. It didn't feel like the Earth was moving. And there was no observable parallax in the stars. The writings of Aristarchus have been lost, but other people commented on his writings, so that's how we know about him. I guess the last great Greek philosopher with regard to astronomy was Ptolemy. He was in Alexandria in northern Egypt, and he, quote unquote, wrote the book on astronomy. It had a complex title in Greek, of course, the Greek language. A lot of Europe went into decline centuries later, to a large extent due to, you know, the Great Depression. And a lot of Europe went into decline centuries later, due to, you know, the Great Depression. And a lot of Europe went into decline centuries later, due to, you know, the Great Depression. And a lot of Europe went into decline centuries later, due to, you know, the Great Depression. And a lot of Europe went into decline centuries later, due to, you know, the Great Depression. And a lot of Europe went into decline centuries later, due to, you know, the Great Depression. And a lot of Europe went into decline centuries later, due to, you know, the Great Depression. And a lot of Europe went into decline centuries later, due to, you know, the Great Depression. And a lot of Europe went into decline centuries later, due to, you know, the Great Depression. And a lot of Europe went into decline centuries later, due to, you know, the Great Depression. And a lot of Europe went into decline centuries later, due to, you know, the Great Depression. And a lot of Europe went into decline centuries later, d invasions from first Germanic tribes to the north and then Viking tribes to the farther north. Europe went into a period called the Dark Ages, where there's only a relatively small number of Christian monasteries that still had some books and knowledge, but the Arabic Muslim world was having a golden era, starting roughly around 800 CE. And Baghdad became the place where all kinds of philosophers went, not only Muslims, but Christians and Jews. And they translated a lot of these ancient Greek writings into Arabic. Later, problems came to Baghdad. The Mongol invaders came and, just like the Vikings had done, destroyed everything involving knowledge. And there are some other theological issues in Islam that came along that suppressed philosophy in favor of the Quran only. But by then, Europe was in its renaissance, and translating these what had once been Greek writings, then were Arabic writings. Now they're translating them into European languages, but they kept the Arabic name. They just transliterated it into European languages. It's something like Almagest, which means the greatest. So Ptolemy used a nearly geocentric model, but they had gotten enough additional data on the motions of the planets that the old model with many crystalline spheres was in some difficulty. He was looking for a way to reduce the number of spheres. So the model he came up with is shown on the right here. The Earth is this green sphere or circle, slightly off center from the center of motion of the planets. This dashed line, called the deferent, is the basic path the planet would travel on, attached to that crystalline sphere. And then there was another crystalline sphere that followed the deferent, but rotated not necessarily in the same plane, by the way, as the deferent. In fact, in general, it had to be an inclined plane. So this is called this is a deferent. This is an epicycle. Here's a planet on the epicycle. And the motion of the planet was no longer uniform and unchanging. So to fix that, Ptolemy picked another point off center and not at the Earth, called the equant, from which the motion of the planet was uniform. So this is an attempt to simplify the model. They were getting to have too many crystalline spheres. It was a mess. So this was regarded as a simplification. And this basic model held for well over 1,000 years. And I would add that, and I thought this is interesting, that Ptolemy had access not only to Greek observational data, but to some much more ancient Babylonian data. So even so, over the following centuries, more and more data came in, and it didn't fit this model very well, which ultimately, as this model faced more and more difficulties, set the stage for Copernicus, who came way later, to propose a heliocentric model, a sun-centered model, following the lead of Aristarchus. So Ptolemy, as I mentioned, wrote this astronomy textbook called Almagest, the Greatest. I thought it was fascinating that he then wrote another book on astrology called On the Effects, although the book had some other titles too. For example, it said that the planets could affect someone's life by heating, cooling, moistening, and drying them. So here's the greatest product of ancient Greek astronomy, and it's still heavily mixed with astrology. So, and I think it's interesting that retrograde motion of planets is still thought by some who are into astrology, significantly into astrology, to mean that something bad may happen. I'll jump to the future here briefly to explain how Copernicus fixed this retrograde motion problem. His model was heliocentric, sun-centered. Here's the Earth and its orbit, and Mars and its orbit. He realized that there's a way to explain retrograde motion. I think a lot of you know this, but I'll walk through it as quickly as I can for the benefit of those who aren't familiar with this. I need to say that the closer a planet is to the sun, the faster it needs to go around the sun to not fall into the sun. Mercury goes around the sun in, I think, 88 days, and Venus in, I think, 240 days or something like that. The Earth about 365 days. Mars is longer. Jupiter, Saturn, Uranus. By the time you're out to Neptune, it's on the order of 150 years. I don't remember the exact number, maybe 170. So what matters is that Earth comes around the sun significantly faster than Mars is moving. So when the Earth is here and you look at Mars, it looks like Mars is here relative to the very distant stars. Then from when the Earth is here, looks like Mars is here. Then it looks like Mars is here. But as the Earth passes Mars, Mars appears at point D to have moved backwards. So as the Earth whips by Mars, Mars appears to swivel back for a month or so, and then it picks up its eastward motion relative to the distant stars. So that's an artifact of the fact that we're observing Mars from an Earth that's moving, making Mars only appear to go backwards. It actually keeps moving in a pretty uniform way around the sun. So that was a nice point that explained retrograde motion in a heliocentric system rather neatly. Copernicus still had some remnants of astrological thinking in that he thought that the sun, that the planets orbited the sun in perfect circles at constant speed. But at least he had the right thing in the center of the solar system, the sun, and he could explain retrograde motion. Okay, we're going back to the ancient Greeks. There's a philosopher named Eratosthenes around 200 BCE. He was in Alexandria, northern Egypt. He learned, somebody told him that on the summer solstice, the sun shone directly down to the bottom of a well in a city called Cyrene at local noon on the summer solstice. He realized what that meant. This is a genius moment. Many other scholars wouldn't have realized what it meant because it's not normal for the sun to be able to shine straight down from the zenith. So what he did, here's this city in southern Egypt, and here he is in Alexandria. He, on the summer solstice, probably the following year, measured the angle of the sun at local noon. And he got 7 degrees, or as they didn't have our same system of angles, so he measured it as 1/50th of a full circle, which were, if you divide 360 degrees by 50, you get 7.2 degrees. He measured that angle between the sun and the zenith, straight up. Here's the zenith, here's the sun. He realized that the Earth, I mean, it was kind of pretty well known that the Earth, at least among educated people, that the Earth was a spherical in shape. So he realized that the curvature of the Earth caused the sun to be at a different angle where he was than farther south. And that this 1/50th of a circle, or about 7 degrees, could be, was 1/50th of the way, all the way around the Earth. That told him if he measured this distance and multiplied by 50, he could get the circumference of the Earth. I've read a couple of stories of how he measured this distance. One story hypothesized that there were men, probably just men, who were professional walkers. They knew how to walk with a very constant length of their step, and they could count their steps and tell how far they'd gone. One story said that's how he found out that distance. The other story was he learned that it took a camel 50 days to go from Cyrene to Alexandria, and that they could travel about 100 stadia per day. That's the plural of the Greek word stadium. So about 5,000 stadia from here to here. So if that's 1/50th of the circumference C of the Earth, you multiply 50 times 5,000, you get 250,000 stadia for the circumference. And they knew that the diameter of a circle was equal to the circumference divided by pi. It's about 80,000 stadia. An issue is that the length of the stadium varied a little bit from one Greek town to the next. But using one ancient definition of the stadium, this result was about 14% larger than the modern correct value of the circumference and diameter of the Earth. I've always thought it was strange that Columbus thought he could sail west from Spain and make it all the way to India, because surely he would have known about this data from Eratosthenes. I read in one source that Columbus didn't know about that, but he had used an earlier rough estimate by Aristotle, which was 40% smaller than the correct value of the circumference of the Earth. And that's why Columbus thought he could make it to India. And in fact, thought he had made it to India, and that's why we have American Indians and so forth. So the fact that Eratosthenes knew that the Earth was a sphere and measured its diameter did not mean that he understood that the Earth rotated on its axis and orbited around the sun. The fact that the Earth was a sphere was known from multiple observations, such as the shadow of the Earth on the moon always has a circular shape. The curvature of the surface of the ocean is evident from watching ships seem to rise up out of the water as they get closer. And when traveling south from Greece, different stars and constellations appear in the sky near the southern horizon, just like we heard people say this evening earlier in this meeting. So here's a diagram showing the situation if you make measurements on the sun on the same day at 2 points north of one north of the other. In the special case that Eratosthenes had, where one of these points, in his case at the summer solstice, was such that the sun on that day at noon was directly straight up at the zenith. If that's the case, and you on that same day do measurements from another point, and you measure the altitude angle A of the sun, then this angle here is a right angle, 90 degrees, so you can calculate B, angle B, and the circumference of the sun equals this distance D times 360 degrees divided by B, right? That's what Eratosthenes did. I wanted to replicate this measurement, but I did not want to have to go down that far south to do it. So I did something that looks a little messier, but it's not really very messy. Here, I've got 2 measurement points. I measured the altitude. This is at my house. So this is in Raid, Michigan. So this is where almost all of my data was taken. I measured this altitude angle of the sun on many different days as it varies. And I can calculate angle B1, just 90 degrees minus A1. And then similarly, I either go north or south from there. I actually went south, but I'm showing it as north to measure angle A2. So I then want to measure delta D, the change in D, and delta B, the change in angle B. Here's B2, B1. You run through the mathematics. This angle change in B or delta B simply equals A1 minus angle A1 minus angle A2. Calculate the circumference. It's this angle, I'm sorry, this distance, delta D, times 360 divided by delta B. Winds up being pretty much the same thing. One important point here, at either of the equinoxes, there's some other place on the Earth where the sun is straight up above the equator. So at either the spring or fall equinox, if I measure angle B1, that is my latitude. So I call that B1 prime. If I measure angle B1 at one of the equinoxes. Here's my equipment. Obviously rather home brewed and crude. A flat piece of wood, some bricks and other things to shim it up, and used a level to get it level in both directions. A metal base to support a steel rod. The steel rod casts a shadow on this paper that's taped down. through the middle part of the day, every 5 or 10 minutes, I make an X at the end of the shadow and write down the time next to it. What I want to do is find the point where true local noon, where the shadow was the shortest, and then I can measure the distance from that point to directly under the top of the rod and the height of the rod, and from that I can calculate the angle. I should say, for those who are not very science or mathematics oriented, don't worry about it if you don't follow everything. Just get the big picture here. So here's a graph of data that I took on June the 4th, 2005. You can see as you get to true local noon, the shadow is the shortest, 34.1 centimeters, minimum shadow length. At about 1:30 p.m. This is in June, so we're on daylight savings time. We're not in the center of the Eastern time zone, so that's why true local noon happens at this time. So a little bit of mathematics, and I can calculate angle A from the height of the rod and the length of the shortest shadow. Several days I did this measurement in my backyard. Then we visited relatives in Kentucky. It would have been better if they would have been in southern Kentucky or Tennessee for this measurement, because my data would have been a little more accurate, the bigger the change in latitude would have been. Here I am setting up my equipment in the driveway. This is a bit of a close-up. You can see the date here, June the 9th, 2005. There's a series of X's and times written down. I calculated an altitudinal angle of this at local noon. So here's the data I got in my backyard. And here's the data point I got in Kentucky. This is a simple sine wave fit to the data. So I could figure out what the angle would have been if I had taken data at home that day. So then I calculate the Earth's circumference. The difference in angle that I measure on the sun is 3.84 degrees. I cheated. I didn't ride a camel all the way to Kentucky to get the distance here. I used a map to find that it's 255 miles in the north-south direction separating us. So I calculated the circumference of the Earth, 23,900 miles, off by about 4%. Pretty good. Here is all of my data. And this is day of the year in 2005. This is the altitude angle A in degrees. Excuse me. Here's the data point in Kentucky. You can get a lot of things out of this data. Here's the autumnal equinox. So on that day, if I take angle A and subtract it from 90 degrees, I get angle B1 prime on the equinox, which is the latitude. So I got 42.44 degrees north. The correct latitude was a little different, 0.3 degrees error. You can also get the tilt of the Earth from these numbers here, 23.46 degrees. The actual tilt is 23.44 degrees, 0.02 degrees error. This next point is rather interesting to me. Eratosthenes' tilt angle was 22/83 of a right angle, or this many degrees. So when I talked about this back in 2006, I said, okay, compare that to the actual tilt. The error is 0.41 degrees. Not bad for considering this was BCE. But a few days ago, it dawned on me that the tilt of the Earth might have been different in 200 BC. So I found a way to calculate it, and sure enough, the tilt was a little larger back then than it is now. So his actual error was only about 0.1 degree, not 0.4 degrees. I thought that was kind of neat. Also from this sine wave fit to the data, I got the length of the year pretty accurately. You can find out the day of each solstice and the equinoxes. I mean, I only took data for 5 months, but you can extrapolate to see like when the winter solstice would be. You can get other things like the Tropic of Capricorn, the Arctic Circle, all that kind of stuff. So that's the data I got on the Earth. Next, measurements of the moon. There's a couple of ways to get the size of the moon relative to the Earth, done by Aristarchus of Samos. The way that I chose to do this, one of the ways they did it was to observe the moon. There's a picture I took through a small telescope during a partial eclipse of the moon. The Earth's shadow is noticeably curved on the moon. So I put this in my computer, excuse me, and played with the diameter of this circle until I got a reasonably good fit. Got the ratio of this diameter to the diameter of the moon, about 2.7, probably plus or minus 5 or 10%. Close to the value Aristarchus got of 8/3, again about 2.7. Copernicus had a diagram in his book that you could correct for something here. Here's the sun, here's the Earth, and here's the moon. Because the sun is bigger than the Earth, the shadow of the Earth is conical. So by the time that shadow gets to the moon, it's smaller in diameter than the diameter of the Earth. You can correct for that effect. You have to know how many times farther away the sun is than the moon is. I'm not going to take you through all the details. If I assume that the sun is about 400 times farther away than the moon is, which is roughly the kind of number I measured, as you will see, then my value of 2.7 goes to 3.7 for the ratio of the radius of the Earth to the radius of the moon. Using the data of Aristarchus and Hipparchus, they thought the sun was much closer, only 19 times farther than the moon is. Their value of 2.7 goes to about 3.5. Not bad. Actual ratio is 3.67. They're all in the ballpark. Once you know the ratio of the size of the Earth to the size of the moon, and you know the size of the Earth, I won't walk you through all the details, but you can find the diameter of the moon. I got 3,330 kilometers for the radius. Actual value is this. My error about 4.5%. You can then get the distance to the moon once you know the diameter of the Earth and the angle here. You can calculate d, the distance, using this simple formula. Using that the moon is about half a degree in angular size in the sky, I calculated that the distance to the moon is about 237,000 miles. That value is correct to the average distance to the moon within 1%, which is pure luck to get it that close, because the moon's orbit is elliptical and sometimes it's noticeably closer or farther away. Finally, how do you measure the distance to the sun? The concept is not very difficult to understand, but measuring it is really, really hard. So the distance to the sun is called the astronomical unit. Aristarchus is the genius who thought of how to do the measurement. He realized that if the sun and the moon are both up in the sky at the same time, there's a big triangle in the sky. And if you look at the moon, wait till the moon is exactly first quarter or a third quarter moon, then when you see the moon from the Earth, exactly half of it will be dark and half of it illuminated as seen from the Earth. When that happens, you know one of the angles of this triangle is exactly 90 degrees. It's a basic thing in geometry that if you know two angles of a triangle and one side, you can calculate the length of the other sides of the triangle. So if you can measure when the phase of the moon is exactly 50%, and you already know the distance to the moon, this side of the triangle, if you can then at that exact time measure this angle, you can calculate the distance to the sun. What's difficult is this triangle doesn't really look this way in the sky. It's super elongated because the sun is roughly 400 times farther than the moon. So this angle is almost 90 degrees. So here's my equipment. 8-inch Schmidt Cassegrain telescope with a special eyepiece in it that I will describe in a moment. A notebook and a pen. When there was going to be a third quarter moon, I got up at 4 o'clock in the morning, set this telescope up, very, very carefully aligned it on stars, and waited for sunup. Right here, the sun is up over here, and this telescope is pointed at the moon. I don't know if you can see it, but there's the moon. Here it is looking through the, excuse me, through the telescope. Excuse me. So I needed to measure the phase of the moon, and I needed a reticle eyepiece to do it. I had a commercial 12.5 millimeter eyepiece with a reticle in it, but the field of view in that eyepiece was too small with this telescope to measure the diameter of the moon. Turns out for other reasons, I had taken a 32 millimeter Plössl eyepiece and made a reticle for it. This is a piece of glass microscope cover slide that I designed this pattern on a computer and etched it into the glass so that you can see this when you look through the eyepiece. So I'll explain what the method I use to get the phase of the moon in a moment. I was going to have to measure the angle between the sun and the moon with high accuracy. If I would have had a sextant, I could have measured it directly, but I didn't have one. So I was measuring the right ascension and declination of the sun and of the moon. And then there's some kind of complicated math that I'm not going to take you through to calculate the angle between the two. So to measure the phase, I measured the diameter of the moon and this distance. When P is exactly half of D, that's 50% phase of the moon. Normally you measure phase as a percent of illuminated area. This is a different definition, but they both give the same thing when the phase is exactly 50%. Here's my data. Here's the phase of the moon versus time of day. Here's 0.5 or 50% phase angle of the moon. And it was that phase a couple minutes after 9 o'clock in the morning. So now I have to look at the data I took on the angle between the sun and the moon at that time to get the angle. Here's the sun-moon angle in the sky. Here's time. At 9.03 hours, I got 89.88 degrees. Almost 90 degrees. So I'm measuring a tiny little difference between this and 90 degrees as accurately as I can. So here we are back to this triangle. Now I know the distance to the moon. I knew when the phase was 50%, so I measured this angle, 89.88 degrees. Putting the numbers in, I get the distance of sun, 112 million miles. The actual distance, as several of you I'm sure know, is about 93 million miles. 21% error. As difficult as this measurement is, I was actually fairly happy with that. My ratio of the distance to the sun divided by the distance to the moon, 474, compared to the right answer was about 400. Aristarchus, his ratio was 19. That number stuck for well over 1,000 years. This is my last slide. The ancient Greeks used reason and the best mathematics and measurement equipment available at the time to conceive of ways to measure the Earth, moon, and sun. While this measurement of the distance to the sun was off quite a bit, it's a very hard thing to measure, and I frankly have a lot of respect for them for how well they did. And it was a lot of fun doing this stuff. Thanks for your attention.
All right. Thank you, Dale. Okay, we have time for a few questions. I'd like to ask one first. I see Greg has some comments also. Dale, you've recreated quite a few historical physics experiments. Which one was the most fun for you?
I'm hard put to say. The two that were the most fun, frankly. I mean, I mentioned one recently when I was about 13 years old, measuring my latitude, where I lived in Toledo, by doing a measurement on the angle of the altitudinal angle of Polaris. Measuring, I mean, when I got into astronomy, I gave a talk to the Warren Club, I think around 1998, where I had determined the orbits of the moons of Jupiter. That was a lot of fun. And then this was a lot of fun. So you get 3 for the price of 1, Diane.
Nice. All right, Gregory, you have a couple of comments, you say.
Yeah, I wanted to just say very interesting presentation. And what I found when I've read about what people did in ancient times, astronomy, science in general, was even more difficult than we would imagine sometimes, because remember back then they were using something like the Roman numeral system. The Greeks had a version of something like that. They didn't have Arabic numeral system like we have today. So imagine trying to do any algebra or calculation manipulation using something like a Roman numeral system. I consider that even a bigger hurdle than, we would ever think of.
I think you're absolutely right. I mean, they had geometry,
Right,
but look how they measured angles,
right. Well,
only as fractions of a circle.
right. And what I was going to say was that when Euclidean geometry was being created by Greeks, they didn't use numbers a lot. They were basically using diagrams and pictures to represent the geometry. They had, logic, but they did things with diagrams and pictures more so, not, equations. And like I said, there wasn't a Roman numeral system until like Middle Ages. So
Correct.
that's what I just thought I'd add.
I think I would underscore your comments, and you're absolutely right. People who try to read Newton's Principia, where he described gravitation and laws of motion, it's incredibly, you had to learn Latin to even read it.
Right.
And it was, very few figures in it. It was all long verbal descriptions. His early primitive version of calculus was kind of hard to follow.
Yeah, it wasn't user friendly, his version of calculus. Yes.
Right.
Yeah.
Appreciate your comments.
Sure. Thanks for the presentation.
Sure.
Do we have more questions? Raise your hand. I'm gonna scroll through here to see if I see anybody. Dale, is there anybody in the chat room on YouTube with any questions?
None have shown so far.
All right. Well, thank you again, Dr. Dale. It did seem like an awfully fun experiment, though I'm still a bit boggled by the concept of professional walkers back in the day. What did they do?
What do you mean, what did they do?
Professional walkers.
They were probably soldiers.
That's what I was wondering. Yeah.
Yeah, their commander would say, tell me how long it's going to take, how far is it to the next fort or city or whatever, and they would pace it off.
Okay. I wasn't sure if they were soldiers or couriers.
Well,
Fascinating.
in today's army, when the infantry goes out for practicing out in the wilderness, they have to be able to not only use a compass, but to kind of measure their steps to determine how far they've gone.
Makes sense. All right. Well, if they've no more questions,
And of
thank you
course,
again.
that assumes no GPS, of course.
Right.
Right. Right.
I was trying to keep that from saying.
Well, my point is, my brother used to have to do those exercises back in the 70s when he was in the military.
I had to do it in the Boy Scouts. They would give us directions, so many paces on this compass bearing and then so many on that compass bearing, not paces, but like 300 yards this way and then so many yards that way, like 7 or 8 different compass bearings and lengths to pace off. It was challenging, especially walking through a woods.
Yeah, and you actually tend to have a stronger leg than the other one, so you could find yourself kind of making a curve.
You had to keep watching the compass half the time.
Yep. When I was in the marching band, you learned how to take I think it was 8 steps for every 5 yards.
Oh, interesting.
Yep.
I wonder if camels back in those days were smaller than the current day camels.
That's a really interesting question, given that we now know how small horses were up until about this 18th century.
I don't know. But 100 stadia per day sounds like a sort of a ballpark number for your average camel.
And that's another good point, Dale. You use the term stadia, which means stadium. How do you think were most of the stadiums approximately the same length during that time, you think? I mean, how else could they calculate that measurement?
Well, the stadium was where they did athletic competitions. Our word stadium is their ancient Greek stadium. Comes from that word. For whatever reason, they were not closely standardized in size. So the definition of the stadium could vary by, I think, at least 20%. The value I used was from the Olympic Stadium, which was kind of a important stadium for them.
Totally.
But I don't know if that's the one Eratosthenes used or not.
Dale, I have a question for you on the material from Aristarchus. You were talking about the fact that there's nothing. How did they come upon it at all, or any of the explanations from it? You're talking about a very long period of time. I'm wondering where it was and how it was uncovered and about when it was.
Well, the later writers would say things. I mean, I didn't see it. I didn't read their stuff, but they would say, of course, Aristarchus had the wrong idea. He proposed this, thus and so, the heliocentric model. We only know about him from things like that.
Okay, but I'm saying
obviously he was wrong, because the Earth is clearly standing still. It feels that way.
Oh, I see.
And look, the stars aren't moving around, relative to each other. Obviously he was wrong.
Yeah. But again, like I said, I wonder where the data comes from when you said that much of it was either destroyed or misplaced or whatever. I'm interested to figure out where the data that he had, which was correct or basically correct, where was it found?
No. He had the same data that the others had. He was interpreting it differently.
What I'm saying, where did they pick up on the interpretation is what I'm saying. You said that much of his data was or much of his stuff was gone.
His writings were gone, where he gave detailed explanations of why he thought the heliocentric model was correct.
Okay.
But the data he used to make his model work was the same data they were using for the crystalline spheres geocentric model.
Got it. Okay. That answers my question. Thank you. Nice job. Dale.
I mean, Aristotle was, like I said, he was
like a god to them. Yeah, no question.
he was
Yeah,
the man, you know,
yeah, that we know.
not just in astronomy, but in fields like medicine, all kind of stuff.
The guy was a great thinker, but he wasn't necessarily on target. Just so that's cool. Thanks again.
Yes, thank you.
Great job, Dale.
Yep, really was a
Thank
great
you.
job.
Yep, thanks.
All right. Well, this is one of those funny months where we have a Macomb meeting right after the week after the Cranbrook meeting. So we'll be seeing y'all next Thursday. Have a happy Valentine's Day weekend, everybody.
Take care, everyone.
Same to all.
Bye.
Bye.